Hello, welcome to our exam prep series where we break down everything you need for WAEC, JAMB, and NECO. Today, we're jumping into a topic that pretty much always shows up on your exams, the application of lenses. This one is a huge part of the optics section in your syllabus, so whether you're dealing with ray diagrams, calculations, or instruments, this session is going to give you exactly what you need to nail those questions. Let's get right into it. Have you ever really stopped to think about it? How do your glasses, or maybe your parents' glasses, help you see things clearly? How does a camera on your phone capture that perfect shot? Or how does a telescope let us see planets that are millions of kilometers away? Well, the magic behind all of it is lenses. And trust me, understanding this isn't just for passing exams. It's about understanding the world around you. And yeah, the examiners absolutely love to ask about it. Alright, so here's our game plan for today. We're going to start with the absolute basics in lens fundamentals. Then we'll tackle the math with the lens formula. After that, we'll see how it all works in real life with optical instruments. And then the best part, we're going to solve real past questions from WAEC, JAMB, and NECO. And finally, we'll wrap it all up with a quick summary and some killer exam hacks. By the end of this, you'll be a pro. Okay, first things first, we need to build a solid foundation. You know, everything else we're going to talk about today really depends on you getting this part right. We're talking about the two main players in the story, the convex lens and the concave lens. So, let's get into it. So, you see here, we have the two main types of lenses you've got to know. On the left, we've got the convex lens, which we also call a converging lens. Just look at its shape. It's fatter in the middle. Its job is to bend light rays inward, bringing them together at a single point. This is the principle behind the magnifying glass and the lens in a camera. Now, on the right, you have the concave or diverging lens. It's the opposite. It's thinner in the middle. It spreads light rays out. This is exactly what we use to correct short-sightedness or myopia. Oh yeah, bring out your calculators. This is where we get into the numbers. But hey, don't panic. It's actually very simple once you get the hang of the rules. The lens formula and the magnification formula. These are your secret weapons. I'm telling you, if you can master these two, you can solve almost any calculation question WAEC or JAMB can possibly throw at you. Alright. Look at this formula. It's going to be your best friend. 1 over F equals 1 over V minus 1 over U. But the formula itself is useless if you don't master the rules, the sign convention. Now you have to listen very, very carefully here. F is your focal length. It's positive for a converging convex lens and negative for a diverging concave lens. Easy enough. Now U is the object distance. For the convention we use for WAEC and JAMB, we always take the object distance U as negative. This is so important. And finally, V is the image distance. If your calculation gives you a positive V, you've got a real image. If it comes out negative, it's a virtual image. Please, 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 write this down somewhere you won't forget. Okay, so once you know where the image is, the next question is always, how big is it? Is it upright or is it upside down? That's what magnification, M, tells us. The formula is simple. M equals negative V over U. Now the sign here is key. If your final answer for M is negative, it means the image is inverted or upside down, which is what you always get with a real image. If M is positive, the image is erect or upright. And the number itself, that tells you the size. If M is 2, the image is twice as big. If it's 0.5, it's half the size. Simple as that. Alright, let's put this into practice with a question that looks like it's straight out of an exam paper. An object is placed 20 centimeters from a converging lens that has a focal length of 10 centimeters. We need to find the image position, V, and the magnification, M. Seriously, I want you to hit pause right now, get a pen and paper, and try to solve this yourself using the two formulas we just covered. Go on, Give it a shot. Okay, are you back? Did you get an answer? Let's solve it together. Step 1. Always list your variables. It's a converging lens, so f is positive. F equals plus 10 centimeters. Now the key phrase, a real image that's 3 times the size. Since it's real, it must be inverted. That means the magnification, m, is -3. So many students forget that minus sign, and it costs them all the marks. Step 2. Use the magnification formula. M equals -v over u. So, -3 equals -v over u. The negatives cancel out, which gives us a nice relationship. V equals 3u. Step 3. Now we take this and plug it into our lens formula. 1 over 15 equals 1 over 3u minus 1 over -u. Again, minus a negative is a plus. So that's 115 equals 1 over 3u plus 1 over u. You find the common denominator, you add them up, and you get 115 equals 4 over 3u. Step 4. Now it's just algebra. Cross multiply. 3u equals 15 times 4, which is 60. Therefore, u equals 60 divided by 3, which is 20 centimeters. The object distance is 20 centimeters. You see, when you follow the steps, it's not so bad. Next up, JAMB. You know, this is a classic JAMB style question. They love to make you think a bit differently. They don't just give you u or v. No. They tell you the total distance between the object and the real image is 40 centimeters and the magnification is 3. This one requires a clever first step. This is a fantastic question. If you can solve this, you are in a really good place. Step 1. Get your data. Again, real image, magnification 3. That means m equals -3. Now, the distance between object and image is 40 centimeters. This means the magnitude of u plus the magnitude of v is 40. So u plus v equals 40. Step 2. From our magnification, we know v equals 3u, which means the magnitude of v is 3 times the magnitude of u. Step 3. Now we substitute that into our distance equation. U plus 3u equals 40. This gives us 4u equals 40. So the magnitude of u is 10 centimeters. Now we apply our signs. Object distance u is -10 centimeters. Image distance v is plus 30 centimeters. Step 4. Now we can finally find the focal length. 1 over f equals 130 minus 1 over -10, which is 130 plus 1 over 10. That works out to 4 over 30. Step 5. Flip it over to get f. F equals 30 over 4, which gives you 7.5 centimeters. Brilliant stuff. And to wrap up our practice, let's look at one from NECO. You see, it's not always about calculations. You have to know your theory too. They're asking, which of these things is not part of a slide projector? This is a direct test of your knowledge of optical instruments. So what do you think? The answer is C, a convex mirror. Let's reason it out. A slide projector definitely needs a light source. It needs a condenser lens to focus that light. It needs an objective lens to project the image onto the screen. And it needs a screen. Sometimes, there's even a concave mirror behind the lamp to push more light forward. But a convex mirror? That would just spread the light out and make the image dimmer. It has no business being in a slide projector. The correct answer is C. Wow, we have covered so much ground. You've done really well to keep up. So now, let's boil it all down into one final cheat sheet. This is the part you'll want to screenshot or scribble down for that last-minute revision right before you walk into the exam hall. Okay, guys, screenshot this. This table is your life right now for this topic. You have the two essential formulas, the lens formula and the magnification formula. But the most important column is the one on the right, the sign conventions. U is always negative, F is positive for convex, negative for concave. V is positive for real, negative for virtual. And M is negative for an inverted real image. If you can burn this table into your brain, you've mastered the calculations. And finally, let me give you some exam hacks, some real game changers. 1. If you have a moment, draw a quick sketch. It helps you visualize what's happening. 2. Before you even start calculating, list all your variables with the correct signs. This is where people make mistakes. 3. Be careful with your algebra. One wrong negative sign can ruin everything. 4. For theory, don't just memorize names. Know what each part of an instrument actually does. And 5. Check your units. Make sure everything is in centimeters or everything is in meters. Don't mix them up. Look, I want you to hear me on this. You now have all the tools, all the strategies you need to tackle any question on the application of lenses. You can do this. Practice the examples we went through, find more past questions, and never ever forget those sign conventions. You are going to smash this. Okay, before you click away, I've got a question for you. When it comes to optics as a whole, what's the one thing you find the most difficult? Is it drawing the ray diagrams? Is it remembering all the sign rules? Or something else entirely? Drop a comment below and let us know what you think. It really helps us plan what to cover next. If you found this lesson helpful, please do us a huge favor. Like this video, share it with your classmates and friends who are also preparing, and make sure you subscribe to the channel right now so you don't miss the next topic. Also, head over to examkp.com for thousands of free practice questions and answers. Let's smash these exams together. I'll see you in the next one.